Okay, so the next topic that I want to talk about, hopefully together with you guys, is the conductors and electric field. What I'm going to do here is I'm relying on your reading. Oh, we have a question at home. I'm not going to push forward if we have a question, so let me pause for a moment. From Fran, what is the difference between the electric fields and the forces by Coulomb's law? Excellent, excellent question, Fran. The difference is this, right? It's a bookkeeping difference, but it also, there's two ways of looking at this. So in our simplest configuration, if we have 2-point charges, I can look at it as, oh, these two objects are interacting by a Coulomb force, F equals K Q over R squared. And there's, say this is my source charge and this is my charge that's being impacted, and this guy exerts a force on this guy. I could also just say, hey, I put down a source charge Q and it creates an electric field, and then I bring in this other charge and it experiences a force that's equal to the magnitude of this charge multiplied by the electric field created by the source charge. It's mathematically identical, okay? And I understand, why are we doing this? What's the point of this? There's one very kind of metaphysical way of looking at this. The problem is, if this guy's over here and this guy's over here and they're exerting forces on each other, how are they doing it when they're not in contact? That was the original, the founders of physics type of problem that they were trying to get around. And the way they got around it is just say, hey, this guy modifies the space around it by creating this electric field. Space now has this electric field embedded in it. And then if I bring in this charge over here, it's going to experience the impact of that electric field that it's immersed in, right? It's to avoid that spooky action at a distance. What we'll also find is that it turns out to really, really make calculations a lot simpler. If you go back to this very first thing that I talked about, the superposition principle, this is an absolute nightmare to calculate anything more than two charges. We did two charges in one dimension. If you want to see an awful problem, look at the problem when we looked at two charges in one dimension. Look at the problem in your textbook. I'm not asking you to be able to do this, but the geometry just for two dimensions becomes horrible. And if you go into three dimensions, it's really painful. So what we'll find is the electric field is not only conceptually a nice topic in that it helps explain this spooky action at a distance, but calculationally, it actually simplifies our life tremendously. You're going to have to take a mortgage on my trust, or I'm going to have to take a mortgage on your trust that you believe me on that. But if we stick only with Coulomb's law, the calculations become really difficult very quickly. And the electric field kind of smooths that out, makes it a little bit easier than otherwise it would be. But good question. I hope that answers your question. Conductors in, Fran, is that okay? Can you give me a thumbs up or a thumbs down, or let me know if that's acceptable?
Yeah.
Yeah, good. Okay. Thank you, Fran. Conductors and electric field. This is our next topic. The electric, and what I'm doing again, I think I started saying this, was I'm asking you to read the book. I'm not going to derive things because we just don't have time and you guys don't like it. I'm putting down two stipulations here. You can look at this as we can prove this from first principles. Read your book and you'll see all the details of this. It's not terribly difficult. It's just a logical conclusion that you can make. Or you can just go into the lab and you can measure this and you can say, hey, I don't trust Professor Slifer. I think that this is not true. And you could measure this yourself and verify whether it's true or not. And that's, the experimental way of just seeing whether these are true or not. The two stipulations that I want to put down on the page here is that the electric field is zero at all points inside a conductor in equilibrium. What do I mean by that? So that's a word salad there that I'm not trying to overpower you with. But I have some kind of lump of metal. This is badly drawn lump of metal here. I come along with a charging rod and I somehow put positive charge on this on this lump of metal. You know, say it's a copper potato or something, some kind of copper lump. What's going to happen, what we'll find very quickly is that charge, it hits the surface, very quickly spreads out through the conductor, and this is at the level of nanoseconds, very, very quickly. So when I say equilibrium, equilibrium is established very, very quickly. Once that equilibrium is established, the electric field inside the conductor is zero. So electric field is zero at all points inside a conductor in equilibrium. And the second part, the second thing that we will notice if we look at the electric field of this conductor is that the electric field at the surface of a charged conductor points perpendicular to the surface. So what I'm trying to do here in this badly drawn cartoon is show you some piece of metal, and the charge, after you've put it on there, is at the surface, and that electric field due to that positive charge is pointing perpendicular to the surface at all points on that conductor. The last part of this cartoon is inside the conductor. I've hollowed out a little space, some kind of three-dimensional bubble inside this lump of metal. And in that three-dimensional bubble inside the lump of metal, the electric field is going to be zero. You could put, you know, 10,000 billion gajillion kilocoulombs on the surface of this potato, and you won't feel any impact of that at all in this cavity, right? It's a very nice feature because this can, you know, although this is a bit abstract in this lumpy metal potato here, okay, we have a question from Catherine. Could you scroll back up briefly, please, when you have the chance? Yes, I can, Catherine. Where do you want me to scroll back up to? To conductors and electric field, or even further? Right there, perfect. Okay, so I'll leave it right there for a moment and then I'll move on in a second. What we're going to find is that this idea of the electric field being zero inside a conductor is quite useful. It's what's known as a Faraday cage. And if I can pop up, well, let me hopefully Catherine was able to catch what she needs from the notes here. I'm going to slowly creep away from this page and get to my next page. Faraday cage. So even though I'm saying here, you know, this basic principle of electrostatics is the field inside a conductor is zero, this can be approximated very, very, very well by even just a mesh or a fence or a mesh box. So we can use this to exclude electric fields from a region in space. And a metal cage is a great approximation in this to a conducting box. What am I talking about? Let me show you a picture here. Hopefully I have a nice picture. So here what we have is some poor kid inside a conducting box here. And this thing is what's known as a Tesla coil. It creates large electrostatic forces. So it basically approximates the creation of lightning. So what you have here is a lightning strike, a huge amount of charge being deposited on the outside of this conductor. The kid happily is inside, safely protected from that huge amount of charge, because all of that charge is going to flow on the surface, and it's going to have an electric field inside this conductor of zero. That's what's known as a Faraday cage. And if I can, I'm going to try to show you a video. If you cannot see this in, please let me know, but or hear it. We're going to try to watch a YouTube video here of a Faraday cage in action.
Serious burns. If they went through your heart, you probably suffered cardiac arrest.
So in order to get video of the lightning striking inches from our face without risking cardiac arrest, we're stepping into a Faraday cage. The continuous covering of conductive mesh conducts current around the outside of the enclosed space, and none passes through the interior. You can even safely touch the thin mesh on the inside. In the same manner, your car may act like a Faraday cage and protect you from a lightning strike. This car, not so much.
Okay. So you guys can Google YouTube videos just as well as I can. So I'm not going to show the whole video there. But you see that this can have a very nice practical application, in the sense that I have a region of space, say the inside of my car, that I don't want any electric fields from lightning strikes. When I was a kid, I was told that I was safe inside a car because it had rubber tires. You're actually more safe because of this, metallic enclosure that is protecting you. And we have a comment in the comments. Peyton says, "I've been in one of those. It's pretty interesting." That, if you have video of that, Peyton, you should share it with us at some point. That is, I'm glad you survived in the electric field equals 0 region of a Faraday cage and was not struck dead. Also, another nice application of this is, for the people in the class that like to work on their own computers, you get RAM or you get some kind of motherboard or something that you want to, put into your computer. It comes in these little electrostatically protected bags. What is going on there? Those bags are conductive, so that any charge, if you come along after, rubbing your feet on your fuzzy slippers on the wool carpet, and you work up a charge, and then you touch this, it's going to hit the conducting bag, flow around, and inside that bag, because the bag is conducting, you're going to have an electric field of 0, and your component is going to be safe. So this, you can imagine, is quite nice. All kinds of application in radio transmissions, and if you want to protect yourself from the electromagnetic waves of the RF spectrum, you can create these Faraday cages. Really nice application of this simple concept. So I'm going to have to pick up the pace here because Dawn has something that she wants to show you at the end. So let's move on to our next topic, which is uniform electric fields. I want to introduce this idea of a parallel plate capacitor. Our most simple model, we can complicate this as we go along, but our simplest model is a parallel plate where we have 2 thin sheets, and I've placed a positive charge on one of these sheets and an equal and opposite negative charge on the other. They are separated by some small distance d, small in the sense that these 2 plates are very close together, and they have a cross-sectional area A. When I do this, this creates, if I look at this now on the side, I have my 2 parallel plates on the side like this, the electric field in that region is going to be very uniform, right? It's always going to point from the positive plate to the negative plate, and it's always going to have the same magnitude, and the actual configuration of the plates is not so important. So I drew out a picture of a square plate or a rectangular plate. Here's an idea of what a circular plate might look like, and the actual shape is not so important. What we're going to find is in the region between those plates, the magnitude of that electric field is easily calculable. It points from positive to negative plate, and it's proportional to the charge, Q. I want to take either the Q that's on the positive plate or the Q that's on the negative plate, not the sum or not the, 2 times this. Pick either of the magnitudes because they're equal and opposite, and the cross-sectional area of that plate, and I've got the capacitor electric field inside there is going to be proportional to that charge over area. The unit of proportionality is a new ugly constant that we are introducing called epsilon naught, and it's related to your old friend Coulomb's constant by 1 over 4 pi times this K that we saw in Coulomb's force. The numerical value of it, which I don't ever need you to memorize these things, but I do want to show you that, the number is 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. Your exercise after this class is done, or just on a piece of paper right now, is to convince yourself that these units make sense. If I want my electric field to come out, if this charge is in coulombs and this is in meters squared, then my units of this epsilon naught has to be equal to this weird mess, coulomb squared per Newton meter squared, if I want my electric field to come out with newtons per coulomb. Okay, units, they're tedious and they're boring, but they also save us a lot of trouble if we check them first. Okay, so what was I saying? What was I saying? So this is I can calculate that magnitude. The direction goes from positive to negative. And I think I summarized, I said this all in words, but just summarizing it all together. Is Q the absolute value, Jacqueline? Yes. Yep, and Dawn already is answering that question. We want that D to be much smaller than A in the sense that we want these parallel plates to be very close together for this, but not touching, for this to be a valid equation. And the shape will work, whether it's square plates, circular plates, some kind of weird, you know, as long as they're similar in shape or identical in shape, and the area of the two are the same, you're going to get this nice simple formula. So the last thing I want to introduce, and then give Dawn the 10 minutes at the end here, is this idea of forces and torques. So if I have a charge in an electric field, I come along and I put a charge down here, and the stipulation of this problem, I'm saying that somehow I've created an electric field of 100 newtons per coulomb, right? I come into the problem, there's a region of space where there's 100 newton per coulomb electric field. I put a charge in that electric field. I want to figure out what's going to happen to this charge Q, right? Well, I have this formula here. The force on this charge Q is equal to Q times E. That's the definition of what the force in an electric field is. And I know that if the charge is positive, it's going to move along the electric field lines. If it's negative, it's going to move opposite the electric field lines. So let's make this a little bit more specific. I come along with an electron. An electron is a fundamental particle. Each one of them is identical, and every single electron in nature comes with a basic unit charge of negative 1.6 times 10 to the negative 19 coulombs. Any electron you ever find in nature is always going to have this charge. So I put this negative charge with this absurdly small amount of charge into that electric field. I want to know what's the force going to be. The force is going to be that charge, negative 1.6 times 10 to the negative 19 coulombs, times 100 newtons per coulomb. And all this gives me is negative 1.6 times 10 to the negative 17 newtons. My units come out in newtons, so I know I have a force. I've got a negative force. What does that mean in this context? Well, go back to my picture. It means that the force is going to be in the opposite direction of the electric field. And that goes back to my initial understanding of what happens when I put a negative charge in an electric field. It travels against the direction of the electric field lines. If we had put a positive charge in, it would have gone with the electric field. We put a negative charge in this time, so it goes in the opposite direction of the electric field lines. Okay, so there's just a short numerical example of what we would do if we knew the electric field and we want to figure out what the force would be on a charge placed in that electric field. The last kind of interesting topic that I want to talk about is a dipole. So we talked about this idea of a positive and negative charge. They're at some fixed distance. You're to imagine, you know, the simple model in your head is I take a wooden stick and I paste a positive charge on one end and I paste a negative charge on the other, so that they can't get any closer or further apart. But they are free to kind of move around in space in as long as the distance between them stays the same. And what's going to happen if I put this in one of these uniform electric fields, say in between a capacitor plate? So I have a nice uniform electric field. It has the same magnitude everywhere. It's always pointing in this direction. The net charge of this dipole is equal to 0 because I have a positive here and I have a negative here. So I know the total force is going to be equal to 0. The total force here is going to be equal to 0, even though I have an electric field, because overall the charge is 0. But something interesting can happen in this system, in the sense that if I dig down deeper, this guy experiences a force in the positive direction along the electric field. And this guy, because he's negative, experiences an equal and opposite force along the going against the electric field in this direction. So what's going to happen is these guys are, you know, if I have my positive charge here and I have my negative charge here, this guy's going to have a force going that way, and this guy's going to have a force going that way. And if I look just a moment later, what's going to have happened is these guys will have rotated. This one will be pulled in that direction. This one will be pulled in that direction. And if I come back even a moment later, what's going to happen is this positive charge is going to be pulled all the way in this direction. This negative charge is going to be pulled all the way in this direction. And this dipole is going to line up with the direction of the electric field lines, with a positive charge along the electric field line and the negative in that direction. And then they stop. And then it stops, and it's just aligned in that direction. And this turns out to be really, really interesting phenomenon that underlies a lot of interesting biological and physical processes whenever you have a system that has this dipole separation of charge. So let me pause here just for a moment. I'm going to hand over to Dawn in just a moment, but I laid a lot of information on you guys in a little amount of time, and I want to be sympathetic to that. If you have a question, please hit me in the chat or just speak up on the audio now. Okay, I'll take that as everything's okay. And Dawn, do you want to take over now?
Yes, I can take over, but folks should still feel free to ask Carl questions in the chat. Just be clear if you're asking Carl or me. That'll help us out. Okay, Carl, if you could stop sharing.
Yep, there you go.
And then I'll start sharing. So I just wanted to end this lecture with some examples of dipoles and capacitors that you may have encountered already in your courses. So let's see. So first off, water is one of the most important dipoles in the world. I think that's a fair statement. So remember, we've got water is 2 hydrogens and an oxygen, and it turns out that the hydrogens are slightly positive and the oxygen is slightly negative, and that's because the electrons tend to hang out closer to the oxygen than the hydrogen. So we have a permanent dipole here, and it has a fairly permanent shape and distance. So what are the consequences of water being a permanent dipole? And one of them is hydrogen bonds. So hydrogen bonds between 2 molecules are relatively strong bonds. And in this picture here, I hope you can see my cursor. Let's see, I want to keep the chat window open so I can see what's going on there. So here's one water molecule and another water molecule, and the slightly positive hydrogen then forms a hydrogen bond with a slightly negative oxygen. And this turns out to be a fairly strong bond between molecules. It's not nearly as strong as the covalent bonds here. So one of the implications of this is the specific heat. So the specific heat, we haven't done this in a while, but the specific heat tells us how much energy it takes or how much heat it takes to increase the temperature of 1 kilogram of some stuff 1 degree C. And if you look at these numbers here, you can see water has the largest out of all of these substances given. And why is that? It's because water is relatively light. So in 1 kilogram, there's a lot of hydrogen bonds that need to be altered or stretched, if you like, to increase the temperature. And that's why water has such high specific heat. And one of the implications of this is that water moderates temperature changes on Earth is because if there's a lot of energy dumped in, that energy goes to raising the temperature of water, but not by so much. So water is a temperature moderator. It keeps the temperatures from being very variable. One of the other things that happens because of those hydrogen bonds is there's large cohesion between the water molecules. So there's a large surface tension on water. And here we have a picture of an insect on the water. And you can see that even though this is a very light organism, it's clearly making an indent in the water, and that changes the surface tension and allows the water to support the spider's weight. And another use is being able to move water, sap up trees that are, oh, what is it? I think it's 100 meters is some of the largest trees. And that's, it has to be the cohesion between the water. It can't be the atmospheric pressure or pressure differential that does that. And lastly, water is really good at forming solutions. And so what's a solution? If you put salt, which is NaCl, in water, though the Na and the Cal will break apart into the ions, Na being positive and Cl being negative. And I want to go to the next page because I want to connect with what Professor Slifer said. So this chlorine molecule, these three arrows are indicative of the electric field of the chlorine molecule. And water might have originally been in any position around the chlorine, but as Professor Slifer just showed, the water will rotate until it's in this position where the positives are in the direction, the positives rotate, of course, so that it's closer to the negative chlorine atom. And then once they rotate like this, they'll stay. And just the opposite happens around the sodium, is the water will rotate till the hydrogen's away, far away. And this ends up giving us fairly stable, these are called hydration shells around the chlorine and the sodium. And so it's a very good solute. Then I want to move on to capacitors. So just to re-say what Professor Slifer already said is a capacitor is a place where the positives are separated from the negative charges. And in between, you'll have a constant electric field. And so one of the examples is a cell membrane. A cell membrane inside a cell. So this will be familiar to most of the life science students. For those of you that are not life science students, you can tune out, but just be aware that inside a cell, because of all the ions, it tends to be more negative inside and more positive outside. And what this means then is that the cell membrane acts as a capacitor, and there's a constant electric field across here. And I think probably in the next class, Professor Slifer is going to introduce something called electric potential, which is a kind of potential energy. And across the cell membrane, the potential energy difference tends to be about minus 40 millivolts to minus 80 millivolts, with the inside being more negative. So we'll talk more about that later. And one of the most famous applications of electrostatics inside an organism is the action potential and the change of the action potential down an axon. And a nerve signal, a nerve signal is really the change of that potential as you go down the membrane on an axon. So we won't be doing this because it's fairly complicated, but hopefully what we'll do is give you all of the physics that you need so that when you go into a physiology class, you'll have the physics in place, and then you'll get to learn a lot more about the physiology. Another example, for some of you I know had done gel electrophoresis. And the setup is really a capacitor again, because you've got a net negative charge on the cathode and a net positive charge on the anode. which means there's a constant electric field in here, so that when you put segments of DNA that have a charge on them, a negative charge, they'll feel a constant force as they move across. And because it's well characterized what that electric field is, you'll be able to identify different sizes of DNA molecules. So that's an example. And then lastly, there are lots of uses of capacitors. One is to store energy. So for example, defibrillator paddles, you need a whole lot of energy in a very short period of time. And one of the ways to do that is to store energy in a capacitor by storing charge on the capacitor. So it's just like a bank account, except for energy instead of money. And the same goes for car audio systems. If you want a really loud sound, you can get all that energy by storing it in capacitors. You can also steer charges in an inkjet printer, which is kind of old school, but there you go. And to accelerate charges in a mass spectrometer. So capacitors are really very ubiquitous, both in organisms and in our daily life. So hopefully that gives you some examples of things to think about. So I think class is officially over. I'd be happy, Carl and I'd be happy to stay for a few minutes if there are questions, either about what I've said or what Carl said. But otherwise, Carl, class is dismissed, and we'll see people Wednesday.
Sounds good.
All right. Good to see people again.
Hi there. I actually have a question about the homework.
Okay.
I was wondering if there was any way we could have more attempts on the homework, as I feel like as if I'm more likely to get it wrong due to our circumstances.
Yes, certainly.
Okay. Thank you.
And then Owen's asking if there'll be a practice packet. So the plan is, again, just like last time, next Monday, we'll have a set of practice example questions for group work. So that's the plan. So yes, is the answer. Other questions? Welcome.
Okay, if there's nothing else, we only have 9 people still here, so I think we're gonna end the meeting. Dawn, okay?
Just if 1 second, if you would.
Absolutely.
Okay, somebody, yeah.
Oh, I'm sorry. Okay.
All right, I'm good.
Okay. All right. Goodbye, everybody.